Welcome to our fourth lesson on electrochemical reactions. We'll be taking a look as to how we can go and calculate the cell potential today. Now, under standard conditions, and we'll be discussing the standard conditions shortly, the cell potential is called the standard EMF, or otherwise known as the standard cell potential. Now, this standard EMF or standard cell potential is indicated by the symbol capital letter E, and then it will have a small zero at the top together with our subscript for the cell potential at the bottom. And this little zero indicates that it is at standard conditions. Now, these standard conditions that we are referring to, you would need to know off by heart. They are not given to you at the back of tests and exams on your formula sheets. The first one is the temperature of the cell. The cell must operate at a temperature of 25 degrees Celsius. Now you can also go and write it as Kelvin, and remember, in order to take 25 degrees Celsius to Kelvin, we'll add 273 to the value, and that will then end up giving us a Kelvin value of 298. So it's either temperature of 25 degrees Celsius, or you can refer to it as 298 Kelvin. Secondly, your electrolyte concentration, and remember, the electrolyte is that solution that contains the ions that can be broken down via an electrical current, and this must be 1 mole per cubic decimeter. Remember, mole per cubic decimeter is the unit for concentration, and it must be 1 mole in each case. And lastly, pressure must be at 101.3 kilopascals, or also it can be referred to as 1 atmosphere. So these are my standard conditions: temperature of 25 degrees Celsius, electrolyte concentration of 1 mole per cubic decimeter, and pressure of 101.3 kilopascals. Only under these standard conditions we will be able then to use our E cell values given on our redox table. Now, on your redox table, as you would have noted on the right hand side, you'll find these E values. And they start here from a very high negative value, and they decrease until they eventually get to a point where you're going to have 0, which is hydrogen, and then we increase in size again positively wise until we end up with fluorine having the greatest positive value at the bottom. Now, that in this case is though obtained under these standard conditions. If those three standard conditions were not met, then these values cannot be used in order to calculate our cell potential. Now, you would have noted that our hydrogen is a 0 value here in the middle. We're going to take a look as to why hydrogen is 0 and how did they actually get to all of these values given on the right hand side. Now, you would note that we'll be referring to this hydrogen as the SHE, and that stands for Standard Hydrogen Electrode. They've decided to make use of hydrogen and compare all of the other values to hydrogen. So they've taken every one of the substances that you see in your redox table, and they've combined it with hydrogen to see, will it rather lose electrons to hydrogen, or will it rather gain electrons from hydrogen. Now, what they've done is they've made use of a typical galvanic cell, where in the 1/2 cell they'll be having the hydrogen reaction occurring. Now, the way that they do that, you'll see there's an almost type of inverted test tube, and there will be hydrogen gas at 1 atmosphere being pumped into this test tube, and this test tube is submerged into a solution that contains hydrogen ions. Now, right at the bottom though, there is a piece of metal, in this case it's platinum. And this will just help the reaction to occur, and you'll see that there will be bubbles forming on this, obviously, as the hydrogen gets reacted with this platinum. On the other side though, they would have placed in any substance. We just made use here of M, but it could have been any specific substance. It could have been the sodium or the zinc or the nitrate ions or the sulfate ions. Any other one of the substances on the redox table was then placed on this half cell. And then they were able to determine whether electrons were going towards the hydrogen or were they leaving from the hydrogen, and that would then have to determine whether it would have ended being a positive cell potential or a negative cell potential. Now, the formulas that we can be making use of in order to calculate the cell potential is given to you on the formula sheet. There's three formulas. You can either go and say E cell, standard cell, is equal to E reduction minus E oxidation, or cathode minus anode, or oxidizing agent minus reducing agent. Now it's given to you in this fashion, and this makes it actually very nice for you. That means that you can go and take a look on your redox table, or in this case the formula sheet at the back, and you would note that reduction means the same as cathode, which means the same as oxidizing agent. And on the other hand, oxidation means the same as anode, means the same as the reducing agent. Now let's go and take a look at an example to go and calculate your E cell. We can see from this reaction our zinc went from a 0 state to a 2+ state. That means there is an increase in oxidation number and therefore undergoes oxidation. Our copper 2+ though goes from 2 to a 0 state, and that means to us copper underwent reduction. So using our formulas, you can pick any one of those formulas to make use of. They mean exactly the same thing. I'm just going to decide to use reduction minus oxidation in this case, and you could have already seen that we figured out that our reduction was the copper one. Copper 2+ going to copper. Now let's go and take a look on my redox table what is the values. And the value for our copper will be 0.34 as indicated on the table. Note that it's a positive value. And it's important to always use the value with the sign, whether you read this reaction from left to right or right to left, doesn't matter, you always use the sign as is. So copper is positive 0.34. So that means that we'll be having 0.34 positively minus that for the oxidation, and our zinc in this case is the oxidation half reaction. It's got a value of negative 0.76. So we must make sure that we include the negative inside this value. Now 0.34 minus negative 0.76 ends up giving me a positive value of 1.1 volt. Now the positive means that this is a spontaneous reaction and is thus seen as a galvanic cell that occurred. Remember, we said that some of our characteristics of a galvanic cell was that it has a positive cell potential, and that indicates also to you that it is a spontaneous reaction that occurs. It will give off energy of 1.1 volt. Now let's just quickly take a look how chemical equilibrium plays a role in these electrochemical reactions. As this reaction proceeds, going from my left to my right hand side, which is the forward reaction, obviously we'll form more Zn2+ ions and the copper 2+ ions will decrease. Now if you can remember again what our chemical equilibrium was all about, is Le Chatelier stated that the chemical equilibrium will always like to be re-established by opposing the change done to it. So if the copper 2+ decreases, the chemical equilibrium would have liked to replace it, and then it meant it would have liked to favor the reverse reaction. Now whenever the reverse reaction is favored, this means then that your EMF produced will be decreased. Let's go and take a look at what would happen if we then, as the reaction proceeds, have an increase in the Zn2+. Now an increase in the Zn2+ will also lead to the system wanting to favor the reverse reaction, and the reverse reaction will cause the EMF to decrease because we're forming less and less of my products on the other side that needs to help produce this EMF. Now that means that as this reaction proceeds, as the copper ions decreases and the zinc ions increases, the EMF will decrease until it eventually reaches a 0 volts. Because we start off with 1 mole per cubic decimeter standard concentration of my electrolytes, we would obviously note though that as this reaction proceeds, we will have less than 1 mole per cubic decimeter after a while, and more than 1 mole per cubic decimeter of the zinc ions after a while. On the other hand, if you get to the point where you start to favor the forward reaction will always lead to an increase in your EMF values. So just make sure that when a question is given to you, whether the forward or the reverse reaction would be favored, because if the forward was favored, it will always increase your EMF value, that means your cell potential value, and if the reverse is favored, it will decrease it. Now let's just take a look at one more example. We're going to have then our sodium and our chloride. In this case, sodium goes from a 1+ to a zero state, which meant in this case that it had a decrease in the oxidation number, and thus reduction occurred. Our chloride, on the other hand, chloride ion goes from a negative also to a zero state, but in this case it means an increase in the oxidation number, and thus it undergoes in this oxidation half reaction. So when having to go and write and fill these values into my cell potential formula, we would first fill in the reduction half reaction and then the oxidation. So let's go and take a look on my redox table what the values are. Sodium, which in this case is my reduction half reaction, has a value of negative 2,71. Sorry, let's just do that again. My sodium, which is my reduction half reaction, has a value of negative 2,71. My chloride, which is my oxidation half reaction, has got a value of positive 1,36. Now it's important to keep your positives and negatives within brackets, and you'll see in this case we're going to end up with a negative 4,07 volts. Now a negative, and remember this was an example of our electrolytic cell, indicates to us it's an electrolytic cell and it is a non-spontaneous reaction. For this reaction to occur, we will need to go and put in 4,07 volts of energy before it can take place.